You ever just look up at the sky and wonder why blue? It's got to be one of the first big questions we all ask as kids, right? But the answer, well, it's this incredible story of physics playing out on a massive planetary scale. So let's break down this amazing light show that happens every single day.
It's definitely not just one color, is it? One day it's a brilliant deep blue, the next it's a fiery sunset red, or maybe a hazy washed out white. It's a constantly changing canvas. So what's going on up there? What's the secret behind this incredible performance? Well, let's find out. To get to the bottom of this, we need to look at the two main characters in our story, the sunlight coming down and the atmosphere it has to travel through. How these two interact, that's the key to everything. And here they are. On one side, you've got sunlight, the source of all the light, all the color. And on the other, you have our atmosphere, this huge ocean of air that the light has to journey through to reach our eyes. And believe me, their meeting is where all the magic happens. Okay, first up, let's talk about sunlight. To our eyes, it looks, white or yellowish, but it's actually hiding a whole rainbow of light inside. That's right, sunlight is literally a mix of all the colors you see in a rainbow, all bundled together. And each of these colors travels as a wave. You can picture blue light as these short, kind of choppy, high-energy waves. And then you have red light, which travels in these long, lazy, stretched-out waves. This difference in wavelength, it is absolutely crucial. Remember that. All right, now for our other player, the atmosphere. It looks totally empty, right? But it is packed with tiny gas molecules and other particles. For a little photon of sunlight trying to get through, it's like a chaotic, cosmic game of pinball. And that game has a name. Scattering. It's just a fancy word for light hitting a particle and getting bounced off in a new direction. This one simple idea, this is the key to understanding the entire color of our sky. And here's the biggest clue of all, you guys. The size of the particle that light hits determines how it gets scattered. When light hits tiny little air molecules, you get something called Rayleigh scattering, which is super effective at scattering those short blue light waves. But when light hits bigger things, like dust or water droplets, you get Mach-Zehnder, which scatters all the colors pretty much equally. This single distinction is the secret to the whole shebang. Okay, we've got our clues now. We know sunlight has a whole spectrum of colors, and we know there are two different ways those colors can get scattered. We are officially ready to solve our first case, the classic blue daytime sky. So picture this. Sunlight streams into our atmosphere. Those long, lazy red waves, they tend to just plow straight on through. But the short, choppy blue waves are the perfect size to get bounced around by all the tiny nitrogen and oxygen molecules in the air. They get scattered in every single direction, up, down, sideways. So no matter where you look in the sky, you see this scattered blue light coming at you from everywhere. And that's it. That's why the sky looks blue. And get this, the difference is not small. A photon of blue light is about 8 times more likely to get scattered by an air molecule than a photon of red light is. That is a huge bias. It's that powerful preference for blue that literally paints our entire sky. Okay, so that totally explains a beautiful blue afternoon. But what about at sunrise or sunset? You know, when the sky just explodes with reds and oranges? What changes then? Turns out the only thing that really changes is the angle. When the sun is way down on the horizon, its light has to travel through a much, much thicker slice of the atmosphere to get to you. And by the time that light reaches your eyes, almost all of the blue light has been scattered away off in other directions. So what's left to make that final journey straight to you? You guessed it, the long, lazy waves, the reds, the oranges, and the yellows. All right, so blue skies, solved. Red sunsets, solved. But what about those other days? The white, hazy, or just plain gray skies? For that, we need to bring in our second type of scattering. Remember Mach-Zehnder? This is what happens when sunlight hits particles that are much bigger than just gas molecules. We're talking about things like the water droplets in clouds, or dust and pollution floating in the air. These bigger particles, they're not picky. They scatter all the colors of light, red, green, blue, you name it, pretty much equally. And when all those colors get scattered together and hit our eyes, they just recombine into white or gray light. And you can see this happen in real time. This research points out that on days with a lot of pollution, the sky's character completely changes. The direct sunlight might look more yellow, and the sky itself loses that deep blue color and becomes this hazy, grayish white. It is a perfect, real-world demonstration of Mach-Zehnder hard at work. And that's the really beautiful part of all this. These simple principles, light waves of different lengths, meaning particles of different sizes, they don't just explain the color of the sky. They create all sorts of other wonders, from the perfect arc of a rainbow to that shimmering halo you sometimes see around the sun. Which really makes you wonder, doesn't it? If this simple act of light getting bounced around by our atmosphere can create so much beauty and so much variety, what other secrets are hiding, right in plain sight, in the light that fills our world every single day? It's something to think about the next time you look up